Hi all, now we'll discuss about some more concepts about instruction set architecture. You all know about the computer architecture or hardware is related to programming. That is, if this is my program, this program is dependent on hardware. This program is execution of a program depends upon the hardware. Why? Because this hardware includes native data types. Hardware includes native data types. So the native data types means example for native data types are character, integer and float. In general, the character takes 1 byte of memory, and of course it is dependent on the hardware. So that way, if you declare on one computer which has hardware configuration 1, and if you develop a program on one computer which has hardware configuration 1, and if you try to execute a program on hardware configuration 2, here the memory allocation for the native data type can be entirely different. For example, the hardware 1 might allocate 1 byte for character, maybe it can allocate 2 byte for the character in hardware 2. So this is an example that program is entirely dependent upon the hardware configuration. So it entirely depends upon hardware configuration. So this is an example of a native data type, and the example of a native data type where character, similarly we have integer native data type. Integer native data type can have short and int, signed int and long int. So these are the different types in integer data type, that is native data type. And next I have float. So in float I have float data type and double data type. So these are the different types of data types. So it includes native data types, instructions. It also includes some instructions and registers and some addressing modes. It also includes some instructions. So it also includes instructions and registers. So when I say registers, registers are basically related to special purpose register such as program counter, instruction register, stack pointer register, MAR register, MDR register. Like that, we have different types of registers, and of course addressing modes. So the addressing mode, what it it says, the addressing mode says that if the memory contains some operands, if an instruction, let's take an example, add a comma b. If this is an instruction, this is called opcode, and these are called operands. So these operands can be present within the instruction itself, which is called immediate addressing mode, or the value can be in registers, or address can be in the register, or value can be in the memory, address can be in the memory. So just to find out what are the operands available for an instruction, what is its location, what is its address, and what about its value. Finding all these things is nothing but addressing mode. Next we have memory architecture. Memory architecture. So when I say memory architecture, this memory architecture is related to how memory is organized. If you take main memory, how main memory is organized, whether all, if there is a multiprocessor system, all processors share common memory, or each processor P1, P2, P3 and P4, each processor can have one local memory. Each processor can have one local memory. This is called memory architecture, how the memory is organized. Next we will see an interrupt. Remember, interrupt is a kind of disturbance to the processor. Interrupt means some kind of disturbance to the processor. So what is the purpose of this disturbance means? When processor, if this is my processor, when it is executing some instruction 1, if it receives interrupt request signal from some IO interface, then it will complete the execution of the current instruction, and then it will send interrupt acknowledgement signal to the IO device, and then this processor, what it does, it stores, it copies content of PC to some stack. What PC contains? PC contains the address of next instruction. So when it services particular interrupt, when it executes a particular interrupt called interrupt service routine, it has to copy the content of PC to stack. This is called an interrupt. And another concept, exception. So one should have a clear understanding what is meant by exception and what is meant by an error. Remember, exception means some kind of error that can be handled by program itself. Error means program cannot handle. Program cannot be handled. This is called exception handling and this is called error. And example for exception. And example for error. Example for exception is, let's assume A by B, but before that B got 0. This is called divide by 0 exception. This kind of exception is called divide by 0 exception. For example for another type of exception is, for example, if you try to open a file which doesn't exist, then it is called file not found exception. So it is a file not found exception. Or example for error is hardware failure. It's an example for error which cannot be handled by the program. So this instruction set architecture means it should include instructions for how to declare, how to develop, or how to declare a native data type, some set of general purpose instructions. The instruction set architecture should contain how it should access registers, what are the addressing modes available for that instruction, and similarly how the memory can be organized with respect to these instructions, and what is meant by an interrupt, what is mean how to handle the instructions related to exception handling, and how to deal with external IO devices. So when I say how to deal with external devices, this is my processor, this is my main memory, this is my secondary memory, these are the IO interfaces. And these IO interfaces can directly send some signal to processor. This is called interrupt request. So you should understand some instructions or design instructions related to external IO. Next, example for registers are program counter, instruction register, stack pointer, PCIR stack pointer, and MAR register, MDR register, MAR register and MDR register. Next I have move, add, increment, and these are the some examples of general purpose instructions. Instruction set architecture also specifies the set of opcode. Remember, these are the examples for the opcode which can be decoded by the instruction decoder of the control unit. So the instruction contains two parts, opcode and operand. Opcode and operand. So the opcode part is decoded by the control unit. So the instruction set should also contain the opcodes, machine language opcodes in machine language, and native commands, some native commands. Some native commands implemented by a particular processor. We will see some examples of instruction set architecture. Examples for instruction or famous, well-known instruction set architecture is one is x86, which is one type of architecture which is based on Intel 8086 processor, which is developed in 1978. So this architecture is developed in 1978. It belongs to, remember I said when you discuss about processor manufacturers, examples are Intel processor or AMD processors. So the Intel processor or AMD processor. So the Intel processor family also followed by AMD, which is called x86. In x86 we have x86 64. So this is a 64. 64 stands for 64 bit. It will work for 64 bit, proposed by AMD, also followed by Intel. So first, this x86 processor is developed for 32 bit. Later on, x86 64 is developed for 64 bit data or 64 bit operating system. Next we have ARM. This ARM stands for one type of processor. This processor is available in both 32 bit and 64 bit. It is available both in 32 bit and 64 bit. Initially, ARM is a Acron RISC machine. So here you should understand the important word RISC. RISC stands for Reduced Instruction Set Computer. Yep. This RISC is called Reduced Instruction Set Computer. Next, we have ARM Holding. This is another version of ARM processor. Next, MIPS. MIPS, million instructions per second. It is also available in 32-bit and 64-bit mode. And this is by microprocessor without interlocked pipeline stages. So it is a processor. This specialty of this MIPS processor is that it doesn't have interlocked pipeline stages. So it has the pipeline stages that doesn't have any interlock, any lock in between. That means if you remember the pipeline architecture, if we divide a work into some stages, stage 1, stage 2, stage 3, stage 4, you cannot lock any two stages. That means you cannot deploy any buffer. That means all the time required for all the stages should be almost equal, which is called interlocked pipeline stages technologies. Next, some other well-known instruction set architecture is SPARC. SPARC. It is also available in 32-bit and 64-bit. It is developed by Sun Microsystems. It is developed by Sun Microsystems. And another well-known on instruction set architecture is PIC. It is available only 8-bit, 16-bit and 32-bit. Next we have Z80. So this Z80 is available only in 8-bit. It is developed by very old technology company, based company Zilog. It is developed in 1976. So there are many other extensions for these processors. For example, if you take Intel processor, the extension are like MMX, SSE and SSE2 and AVX. These are the some of the extensions. And extension for AMD processor is 3D. So these are the some of the examples of architectures. Now we should see how a good instruction set architecture should be. It should last through many implementation. That means it should have portability and compatibility. We should understand these two words. One is portability and another one is compatibility. What portability says? Portability says that any instruction set architecture can be implemented on any hardware configuration. If you develop a program based on one instruction set architecture, that should able to execute in hardware 1, hardware 2 and hardware 3. You should able to execute in hardware 1, hardware 2, hardware 3. Next we will see what is meant by compatibility. The compatibility means it should be compatible with any hardware changes, because hardware is not fixed. It is hardware is evolving. It is getting changed continuously. Still this instruction set architecture should be compatible with the hardware versions, version 2, version 2, version 3. This is called compatible. Next, it should be used in many different ways. It should be used in many different ways. That means this instruction set architecture can be used to write programs for servers, programs for desktops, programs for laptops, programs for mobile, programs for tablet. So your instruction set should support to execute or develop a program in for server, program for desktop, program for laptop, program for mobile, and also for tab. It provides convenient functions to higher layer. What is meant by higher layer? Instruction set architecture is basically related to machine level instructions. With your higher layer, it can be any programming language like C, C++, Java. All this has to be converted into this native code. Here it is very important to understand this point. If you write a program in C or C++ or Java or Python, any language you can take, your instruction set architecture, this has to be converted into any high level programming language, has to be converted into instruction set architecture, which is called native important to understand, right? So any higher level layer provides convenient functions to higher layer. So if your C language wants to access a native code, it provides a function. If your C++ wants to access this instruction set architecture code, it is called native clause. It should support some functions and provide and permit efficient implementation at lower layer. So I will draw a picture. What is this lower, higher layer and layer? Here C, C++, Java, Python. This code has to be converted into native code. This is called native code, and this native code has to be implemented in hardware. So this becomes lower layer, these are becomes upper layer, the lower layer and upper layer. So this instruction set architecture should communicate with both upper layers and lower layers. So it has to communicate with the upper layer and lower layer. Now we see some examples that microprocessor that we are going to build will support following two instructions. So the microprocessor, we'll see an example that we are going to build, will support following two instructions. Let's assume there are only two instructions. One is add, other is load. So these are the two instructions. Now these are the two registers RA and RB. Content will be stored in RC. Now this 0 1 indicates that you need to perform add. 0 0 indicates 0 0 indicates that you need to perform add. 1 0 indicates that you need to perform a load. Next, these 3 bits represent RA register, these 3 bits represent RB register, these 3 represent RC, and let's see what are these. These are kept blank. Similarly, this is for add. Similarly, for load instruction, load means load the content to the accumulator. So if you want to load, that means you have to, here let's assume RA is accumulator, load the value of D2 in RA. The first one says opcode 10. Remember, 0 0 stands for add, 10 stands for, these are opcodes. Next, this represents RA since it don't have any second operand, 0 0, and here is value D that has to be loaded into RA register. So these are the two instructions of a microprocessor. So total, if you take, it has 0 to 15. So total 16 bits instruction. Example of a two 16-bit instructions. These are example of two 16-bit instructions. Next we see activating necessary blocks for these two instructions. So here, this is my ALU, arithmetic and logical unit. It receives opcodes from instruction decoder of control unit. It receives an opcode. Next, we have two multiplexers MUX. MUX stands for multiplexer. The specialty of this multiplexer is that it takes multiple inputs and single output. It have multiple inputs, single output. Any one of the input is selected, which is called multiplexer. What this multiplexer is doing, here I have an instruction decoder, and these are the registers. So based on the see the register, there are 8 registers, 1 2 3 4 5 6 7. For that we are using 3/8 decoder. So what this decoder will do, this decoder will take 3 inputs, A, B, C, and it can output 8, 5, 6, 7, 0 to 7, total 8 outputs. So 3 inputs and 8 outputs, which is called 3/8 decoder. So we are using a 3/8 decoder. Based on the input, it will select any one of the register. So ultimately what happens, this 3/8 decoder selects any one of the register R12 or 7. When you select a particular register, that data, for example, if it contains 0, 1, 1, third register R1, R2, R3. If the input is 0, 1, 1, this register will place the data, output goes here. Next time if you send 110, means 5. The register 5 will be sent as a output. So R3, R5 can be selected out of this 8. So in general what happens, if I have some 16 registers, then I need 4 into 16 decoder. Similarly, if I have 32 registers. I need 5 by 32 decoder. So this is about selecting the inputs. These are the very important. Okay, these are the important instructions for registers. Next, we will see what is meant by a micro operation. We will see micro operation. So what is meant by a micro operation? So the digital modules are best described by registers they contain. So what are the registers they contain, and what are the micro operations performed on data stored on those registers? So what are the operations that you perform on the register, which is called micro operation? So remember, any digital module is best described by how many registers it contains and what micro operations. Next, elementary operations done on the data in the register. Example, register transfer language, concise short symbolic expressions such as add and load. So these are the micro operations. How to describe a computer? So we can describe a computer with set of registers and their functions. First, how many registers it contains and what are their functions. Next, sequence of micro operations. What are the sequence of micro operations? What are the sequence of micro operations? Next, controls that initiates and maintains sequence of micro operations, and how to control the sequence of micro operations to be executed, and how to initiate. And today's world, from a programming point of view, assembly is the lowest level we use to define those registers, instructions, and their order of execution. Everything can be best described by assembly language, or you can call it as lowest level language, which is called lowest level language. So this is about some important points about instruction set architecture. So here we see that some set of registers and their functions. How many registers it can contain, like program counter, instruction register, stack pointer, memory address register, memory data register, accumulator, like that.